Right, Pythagoras' theorem. That's to do with right angle triangles. A right angle is 90 degrees, which I'll represent on a triangle by a box like this. The hypotenuse is the longest side in a right angle triangle, and that's directly opposite the right angle. And Pythagoras' theorem, if I class that side as A and that is B, probably best if I just denote that as H, just to keep them all in small letters. So Pythagoras' theorem says that h squared equals a squared plus b squared. The square of the hypotenuse equals the square of a plus the square of b. Right, so that's at the bottom level. That's really all there is to it. I could go off to the side here and mention that there is a thing in science called Stigler's law. And Stigler's law states that no scientific equation is actually named after the person who invented it or came up with it. You know, there's no scientific equation, no theorem or scientific instrument is actually named after the person who invented it. And that includes Stigler's law itself. Stigler did not actually come up with Stigler's law. Now, I mean, this is a bit of a jokey thing, but it's not exactly correct in 100% of cases, but it is correct in quite a few cases. So what I'm really getting down to here is that Pythagoras is not the person to be considered as the originator of Pythagoras' theorem. But at the same time, it does actually indicate that this theorem was actually well known in the times of the ancient Greeks. So that reinforces what I was saying, or what I've already said. There's a lot of mathematics that you do at GCSE level is actually quite ancient. I was going to say a few things about Stigler's law. I'm not too sure whether I should do that. I mean, there's quite a few equations and so on that are named after people who didn't really have anything to do with its origin. And on the other hand, there's equations and so on that are named after one person, where in fact several or many people were actually responsible for formulating the equation. So there's this type of thing, and more generally, you got to be careful about this in trying to form out some sort of history leading from an equation or a law. I mean, for example, there's Hubble's law to do with expansion of the universe. And if you were to expand on that and try and get up some history, giving Hubble sort of the credit for this, that would write out one or two people whose work also played an important part in formulating Hubble's law. And in the present day, you've got a subatomic particle called Higgs particle, and to actually describe that, or the idea of the Higgs particle purely to Professor Higgs as he now is, that would be highly misleading. So you see the general idea. I was just going to say a bit more about Pythagoras as well. Although it's just nominally to do with triangles, it's also actually used to find distances. So, if I've got a graph, this would be represented Cartesian coordinates, okay, where the horizontal axis would be conventionally classed as x, and that would be classed as y. Now, if I had 2 points here, and I wanted to find the distance between them, I tend in general to actually use Pythagoras. I'd consider a line there and a line there. So if I call that x dot and y, not x dot, x prime and y prime, then the actual distance, s squared, would be equal to x prime squared plus y prime squared. Okay, so sometimes you're only doing it, sort of implicitly, but you can see that in that sense, Pythagoras' theorem has got a much more general usefulness rather than just purely, straightforward geometry. So, I mean, this is 2 dimensions. In 3 dimensions, there would be another axis which we would class as z. So Pythagoras would also work in that sense as well. So you'd have a three-dimensional line. You'd have s squared equals, well, I'll just call it x now. Okay. Instead of calling it x prime, I'll just call it x plus y squared plus z squared. And that would find the distance within 3 dimensions. And this, without seeming too grand, this can be transformed into 4 dimensions, or it can be generalized, where you've got something like this. Now, in 4 dimensions, I'm talking about not general relativity, I'm talking about special relativity and so on here. You know that different people will measure different times, and also, different people will also measure different lengths. That's if they're travelling at very, very high speeds. So there's quite a bit of a confusing situation there. Different people measuring times, different times and locations. But if I could just spring back to this for a moment, or probably, centre on this. I mean, if you had a particular object, and you had an object, and you had, say, someone looking at it from this direction, someone from this direction, and someone from this direction. Say it was a stick. The actual x and y and z coordinates that these different people would have, if they were to draw up some sort of coordinate system of their own, their coordinate system would be different because they're looking at it from a different angle. So it'd be slightly chaotic, but what would actually hold it together would be they could apply Pythagoras' theorem and they would all get the same answer. This would be an invariant. So from this seemingly chaotic system of different x, y's and z's, they could get up this invariant, i.e. the distance, which they all agree on. And it's like that in special relativity as well. Different people are measuring different times and different lengths, but when they come to calculate this, which is sometimes called the proper distance, everyone will agree on the same proper distance. So that would be an invariant in special relativity. Everyone would agree on the same amount. So you can see that brings a bit of order to the system. But yeah, I'll mention that in passing, just to indicate that Pythagoras' theorem, when it's generalized, can have quite some powerful uses. Now, when we're dealing with right angle triangles, we can also that's the hypotenuse, remember. Now, if I draw a particular angle in, I'll use theta, which is common. That should be a theta like that. That's commonly used to denote angles. Now, relative to this angle, that would be the opposite, and that would be the adjacent. Okay, opposite and adjacent. If it was the other way around, if I was to draw a triangle like that, now these. Okay, this is a bit off, but these are intended to be congruent, okay? Well, they could be similar. Similar triangles will have identical angles, so that's really what I'm after, identical triangles. But if that had similar, if that had identical angles to that, those two triangles would be classed as similar. If they have also the sides of equal length, or corresponding sides of equal length, they would be classed as congruent. So either way, what I'm really trying to stress is that that's the hypotenuse. If that's the angle up here, I'll call that alpha. Okay, this is still theta. That's alpha. Now, relative to alpha, that will be the opposite, and that will be the adjacent. So the terms opposite and adjacent in a triangle relate to which particular angle you're looking at. And from those definitions, you can draw up various definitions, trigonometrical definitions of a sine. Well, in full, it's sine, cosine, tangent. Okay, that's the names in full. I should also say in passing that tangent has two meanings in mathematics. A tangent could be a line being, how should I say, if you had a line like that, a tangent would be like that. It'd be briefly having the same gradient as that line at a point. So that would be a tangent to that curve. But here, this is a totally different meaning. We're dealing with trigonometry here. So sine of theta, I'll call it theta, equals opposite over adjacent. The cosine of theta would equal, no, sorry, that's wrong. Opposite over hypotenuse, that would be adjacent over hypotenuse, and the tangent of theta would equal opposite over adjacent. So that's a couple of definitions to learn. And we commonly see this mnemonic. This is supposed to sound like a volcano, you know, like Krakatoa or something. But as far as I know, there is no volcano or mountain with this name. But it's supposed to be used as a mnemonic. You've got sine equals opposite over hypotenuse, cosine equals adjacent over hypotenuse, tangent equals opposite over adjacent. Now, at the foundation level at GCSE, you don't really need to know too much more than this, really. You might, for example, use it as an equation. If you had a triangle where you knew what the hypotenuse was, and you knew what a relevant angle was, and therefore you could work out what the sine is, you could look it up on your calculator. You could then set up an equation to find out what the opposite side is, and that type of thing. So that's about the sort of level you would need to go at foundation level. At the high level, you'd use it for quite a bit more advanced purposes. Right, what was I going to say? I was going to say, right, there was something I was going to say there, but I've forgotten what I was going to say. There are standard values. I know something I've forgotten. Yeah, okay, I'll come back to that later, sorry. There are standard values for sines and cosines that you can also consign to memory. Right, yeah, sorry. There is one thing I could say while I think on. Because the hypotenuse is the longest side in a right angle triangle, you can see that sine and cosine have got to be 1 or less. The modulus 1 or less. You know, you can't have the opposite or the adjacent being longer than the hypotenuse. So that's sine and cosine have a modulus of 1 or less. By modulus, I mean I'm accounting for -1 as well. Okay. When I say sine, that means less than or equal to 1. So that could include the negative numbers as well. The -1 has a modulus of 1, and minus a half has a modulus of a half. So sine theta can take any values between -1 and 1. That's what I'm actually saying by this expression here. Right, sorry about that again. Getting back to what I was going to say, these are standard values. Now, for sine, the sine of 0 degrees is 0. Of 30, it's a half. Of 45, it's 1 over root 2. Over 60, it's root 3 over 2. And for 90, it's 1. Some of these you can sort of test yourself by drawing up a right angle triangle and just confirming that these are true. Now the cosine works in exactly the opposite direction. Cosine for 0 is 1. 30, it's root 3 over 2. 45, it's the same. 60, it's a half. And 90, it's 0. So you just have to remember that these are the opposite way around. Tangent is slightly different. The tangent is 0. It's for 30, it's 1 over root 3. For 45, it's 1. For 60, it's root 3. And for 90, it's infinity. As I say, you can get up triangles to just convince yourself of this. I mean, if I've got... if I've got a triangle like that, I mean, again, one rule I haven't stated so far is that the internal angles of a triangle must equal 180. So although you haven't come across triangle, although I haven't actually mentioned triangles before, maybe you might be able to appreciate that if that's 90, then if that's 45 and that's 45, then basically you've got a triangle where that side and that side are equal. Hopefully that's logical. I'm saying that the length of that is equal to the length of that, and that's sort of tied in with the 45 and 45. And when you've got a triangle like that with two sides equal, that's classed as an isosceles triangle. I mean, an isosceles triangle in general, if you've got a triangle like that, you can hopefully, so when you think about it, that angle there is going to equal that angle there. I mean, this can be any angle. I'm not talking about a right angle triangle here. That could be any angle at all. But hopefully you can see that those, by virtue of the fact that this being an isosceles triangle where that side has got the same length as that side, those two angles will be identical as well. But what I'm leading up to here is that if I take the tangent of that, tangent 45, I don't, whatever side that is, I can call it A. That'll be A as well. So that'll be A over A, opposite over adjacent. And that'll be 1. So you can see that's okay. Tan 45 is 1. That's quite logical. When I've got this seemingly unusual result, the tan of 90 is infinity. I mean, basically what you have is that you'll have a situation like this. That's your right angle from the right angle triangle. There's your angle of 90. Now what's going to happen is that those lines are going to be parallel. They're going to go up forever to infinity. And so that's why I'm saying that the tangent of 90 is infinity. Right. As I said, there's one thing I forgot to say before about Pythagoras' theorem. So I'll go back to this now. I'm sorry about the disruption. But I was going to say that certain right angle triangles have sides which can be expressed in terms of integers. One of which is 3, 4, 5. Okay, you got the square of that is 9, the square of that is 16, and the square of that is 25. So hopefully, if you can still remember what Pythagoras' theorem says, that plus that must equal that, and that's what it does. So 3, 4, 5 is a well-known right angle triangle. And one other which you might sort of test for yourself is a 5, 12, 13 as well. Okay, 13 will be the hypotenuse, and 5 and 12 will be the other sides. Right. I'll just finish off here. Find a spare piece of paper. Well, I'll stick it on here. I finished off the section on Pythagoras by going as far as talking a bit about special relativity. I'll finish off this bit about sines and cosines by talking a bit about an identity which you meet most commonly at A level. But I can introduce it now, and I'll say that tan theta equals sine theta over cosine theta. Okay. Now, when I do this, as I say, in an even class or something like that, because people come in at different levels, some people might have learned quite a bit when they were at school and so on. So what I would tend to say is that, okay, if you're happy with this, what we're doing so far, you might have a go and prove this, while I get on with the people who are not too happy with it, which possibly the majority in the class. You can have a go at this. So likewise, you yourself can have a go at this if you want. It's not too difficult per se. You need to work in slightly algebraic form, but you need to start on the right hand side. You need to replace sine theta and cosine theta by their definitions that I've given you, and then you need to use the rules for division. And I mean, there's nothing per se difficult about that. It's just that you need to remember that division, when we're talking about symbols, follows exactly the same rules as division of straightforward numbers. I mean, that's the sort of primary rule for algebra, really. To remember that when in algebra we're dealing with in algebra we're dealing with in algebra we're dealing with letters and that type of thing. But the arithmetic operations for dealing with those letters are exactly the same as the arithmetic operations that we used for numbers. That's the sort of the basic rule to remember right at the start of using algebra. So have a go on that anyway, and see if you can make it equal to the left hand side. You'll need to remember what the formula for the left hand side is as well. So I'll leave you with that, and thanks for staying with me if you're still here, and see you next time.